So today, Naman, Tribesh, Shashank, and I are going to be presenting about the use of artificial intelligence in game theory, which is a field of economics and is widely used in our everyday life. So a game such as chess, poker, checkers, rock, paper, scissors, all of which we commonly play, can be formally defined as a set of players, actions, and strategies, all, where all the players are competing for a final payoff. Game theory, which is derived from the idea of games, is basically a branch of mathematics that is used in typical strategic interaction between different players or agents, all of whom are equally rational in a context with predefined rules of playing or maneuvering with fixed outcomes and payoffs. Every player is considered a rational entity who is selfish and tries to maximize the reward that they themselves can obtain using a particular strategy. All the players abide by these rules in order to obtain that predefined outcome and payoff. Every game has five major characteristics, which can be summed up as zero-sum or non-zero-sum games, simultaneous or sequential games, imperfect information or perfect information games, asymmetric or symmetric games, and cooperative or non-cooperative games. In this presentation, our focus is going to be on imperfect games to try and analyze the mechanism of game theory in such a case. In a perfect information game, every player is aware of the movement of the other player and is also aware of the various strategies that the other player might be applying to try and win the ultimate payoff. In imperfect information games, however, no player is aware of what the other player is up to. Cards are an example of imperfect information games, and so is poker, which we will be taking up in this presentation. While chess is the perfect example of a perfect information game where you know every move of your opponent. A Nash equilibrium, which is one of the major concepts of game theory, can be defined as a list of strategies, one for each player, in which no player can improve by deviating to a different strategy. Nash equilibrium have been proven to exist in all finite games and in many infinite games as well, although finding an equilibrium may be very difficult. It is the best strategy assuming that other players have chosen a strategy and will not change it. In two-player zero-sum games, any player who chooses to use a Nash equilibrium is guaranteed to not lose an expectation, no matter what the opponent does. And hence, the strategy is considered unbeatable. Like in rock, paper, scissors, if you choose rock, paper, scissors with equal probability, the expectation is that you will at least tie. However, with outside of two-player games, even if it can be computed efficiently, it is not clear that playing such a Nash equilibrium strategy would be wise. If each player on such a game independently computes and plays a Nash equilibrium, the list of strategies that they play with one strategy per player may not be the overall Nash equilibrium, and this results in players having an incentive to deviate to different strategies. This can be seen in the lemonade stand game, where Nash equilibrium is for all players to be spaced equally along the ring. But there are infinitely many ways this can be accomplished, and therefore infinitely many Nash equilibriums. If each player independently computes one of those equilibriums, the joint strategy is unlikely to result in players being spaced uniformly along the ring. This can be seen in the diagram shown here. These shortcomings of Nash equilibria outside of two-player zero-sum games and the failure of any other game theoretic solution concept to convincingly overcome them have raised the questions as to what the right goal should even be in such a game. So the aim of our presentation is not to find a specific game theoretic solution concept, but to create an AI capable of defeating elite human professionals in six-player no-limit Texas Hold'em poker. Poker is a multiplayer, imperfect information, zero-sum game, and the algorithms that we use to construct the AI are not guaranteed to converge to a Nash equilibrium outside of the two-player zero-sum game. However, we observe that Pluribus, the AI, plays a strong strategy in multiplayer poker that is capable of producing superhuman strategies while consistently defeating elite-level human professionals.
In 2017, a similar model was created, the Liberatus, that was able to beat 4 of the world's best head of no-limit Texas Hold'em poker pros in the two-player setting. It played around 1,200,000 pounds over the course of 20 days, 2017, and the bot won by a decisive margin. And what's interesting about Livetus is that it was trained entirely from the self-play, and there was no human data that went into the bot. The training was fairly expensive. It is used around 3 million core hours, which would cost around $100,000 in cloud computing credit. And to run at a real time, it would use around 1200 CPU cores. It is still considered a major achievement at the time, but now the question arises, what about more than one, two players? As traditionally, poker is played with more than two players. And there's a lot of challenges going from two-player setting to a multiplayer poker setting. First of all, one of the major challenges is the larger size. So as we add more players, there is exponential increase in the compute power. So a six-player poker setting would require 100,000 times more compute compared to two-player. Then there are game theoretical challenges. When they go from two-player zero-sum to more than two-player, the regret minimization, which was used to compute the strategy for two-player poker, now no longer converges to a Nash equilibrium. We address this problem by using advanced tree pruning, depth-limited search, and modifying game strategy. Next slide, please. Yeah. So we propose a model, Pluribus, for six-player poker game, which plays against 15 top professionals in Texas Hold'em with the bot plus 5 humans at the table. We play 10,000 hands over the course of 20 days, using variance reduction technique to decrease the luck factor to determine the strength of bot with statistical significance. 50,000 US dollars were divided among the pros to incentivize them to play their best. What's interesting about Pluribus is that despite the massive increase in the size of the game, the Pluribus was much cheaper to train and to run than Liberatus. In fact, to train Pluribus on a cloud service like AWS would cost less than 150 US dollars, and running it in real time only used only a 28 core CPU and no GPUs were required. There are some really interesting points that can be drawn from this. First of all, even though there are major theoretical changes that come up when going from two-player setting to more than two-player setting, it is found that the regret minimization technique that were used in two-player were actually quite efficient in six-player no-limit Texas Hold'em. And we think that this suggests that even though there are theoretical challenges going from two-player to more than two-player, even though the regret minimization do not theoretically guarantee convergence to a coarse correlated equilibrium outside of the two-player sum zero game. Nonetheless, we see that these regret minimization technique can compute effective strategies that defeat professional players. Other interesting result is that even though the game has increased in size, the cost to train the bot has decreased by orders of magnitude. And the reason that this can be achieved is by a depth limited search, which we'll talk in the later. Next slide. So the idea behind Pluribus is that we have a massive game, which is simply way too large to be solved in its entirety. So instead what we do is come up with an abstraction of a game, a simpler version of a game, a much smaller version of the game that tries to retain the strategical element of full game as much as possible. The abstraction is particularly detained in the initial part of the games. It approximates how to play in the later part. We are actually playing when we encounter one of the later part in the game where we don't have a fair grain strategy in real time. We do a depleted search which compute the best results, best strategy in real time. This is like chess, where we don't act instantaneously, rather we take 15 to 10 seconds to decide what our next move should be. This is exactly what Pluribus is doing, but in a more complicated way. This search will extend depth to some definite level. Beyond that, it again uses a coarse-grained approximation of what the equilibrium would look like. And this process was repeated as we go down the game when we encounter another subgame. So abstraction. Next we search for a definite limit. First step in the process of shrinking the massive game down to a reasonable size is to do this by using card abstraction and action abstraction. The idea here is that there might be billions of different poker hands in the game like No Limit Texas Hold'em, but we can cluster similar hands together and treat them identically. Then we only have to come up with a single strategy for all of these similar situations instead of unique strategy for each of these different situations. For example, in this particular situation, there might be 5 cards on the board and there might be 2 different poker hands as shown in the figure. We can group them together and treat them identically because they are strategically similar. Even in card abstraction, there is a subtle difference between different poker hands. So card abstraction has its limits. It does not fully capture the equilibrium it should look like. However, it does a pretty good job of approximating it. So using the card abstraction, we can reduce number of possible hands. For example, in the last round of poker, there are over a billion possible hands and it can be reduced to 200 in the blueprint strategy. The strategy does not use search.
Now, once we have this shrunken abstract game, we run something called Monte Carlo counterfactual regret minimization. This is a Monte Carlo version of regret minimization which can be applied to sequential games to find an approximate equilibrium. The idea is that it's an iterative algorithm where the bot plays against itself. It starts completely playing a uniform random strategy, and over time it gradually improves until it approximates an equilibrium. Let's have a look at a couple of iterations of this algorithm to see what it looks like. The algorithm starts by picking up one player and updates regret only for that player, and actions are picked up in proportion to the amount of positive regret on the action. So there is a regret value on every action in the game. This value is updated over time. The regrets all start at 0 and action is picked uniform and random because all the actions have equal regret. So player 1 might pick to go left when we encounter a player 2, as we can see in the next slide. Now we again pick an action proportional to the amount of positive regret, which means uniform and random on the first iteration. Now we can see that it might go left for player 1 again. Maybe now it receives a payoff of $50 in the next, yes. So now player 1 is going to review every decision that they could have made and see what the payoff would have been for those other hypothetical situations. For example, player 1 might see if they had gone right. Instead, they would have received a reward of $100. And so the regret for the action increases by the difference between what they could have received versus what they actually received. So the regret will increase by 50. We are able to obtain these hypothetical rewards because we are in a self-play setting. Player 1 is playing against a copy of itself, so it knows that it had gone right then. Player 2 would have done this and player 3 would have done this, and eventually reward of 100 would have been received. Now if they had gone right, maybe they would have encountered another player. One node in this situation would have chosen to go left. They would have received the award of minus 500. Now, if they had gone right, instead they could have received an award of 100, so the regret of that action increases to 600. Since they would have chosen their award leading to minus 500, if they had gone right, the hypothetical reward for the top node is now minus 500. One can't cheat and see what the rewards are before them, so choose their action so the regret for the right action becomes minus 550 now. In the future, after this iteration is complete, the same thing is done for player 2. Then we'll cycle through all the players, and when we get back to the player 1 actions that have the higher regret will be played with higher probability. Now next. Next slide for the pruning. Yes, thank you. In Pluribus, we use an improvement of pruning in which when there are situations that are consistently giving a negative reward, for example, the top right action at the very beginning is consistently giving a reward of minus 500. Well, it's pretty clear in that case that we don't want to waste a lot of time exploring that branch of the game tree because we shouldn't be choosing that action anyway. And so by using pruning, we can explore those negative regret actions with lower probability and focus more of our efforts on the more interesting, more useful parts of the game tree. And in practice, this speeds up Monte Carlo CFR by a factor of 3. Next slide. Now, coming to counterfactual regret minimization or CFR, which is just like Monte Carlo CFR, except it does not involve random actions. The theoretical convergence bound for CFR is of the order of I into A over T raised to the power 0.5, where I is the number of decision points, A is the number of actions of those decision points, and T is the number of iterations that you've played. So as T goes to infinity, you will ultimately converge to a Nash equilibrium. In practice, now coming to the state-of-the-art model, which is discounted CFR that converges much faster at the rate of T raised to the power 1.5. Now, using Monte Carlo CFR, we can compute an equilibrium and two-player zero-sum games will converge to a Nash equilibrium or a min-max equilibrium, and outside of the two-player zero-sum games, it's only guaranteed to converge to a coarse correlated equilibrium. Although there is recent work suggesting it might converge to an extensive foreign coarse correlated equilibrium, which is slightly stronger solution concept. So it is hopefully a good approximation of what a good strategy should look like, but because this Monte Carlo CFR is being done on an abstract version of the game, it's not giving us an exact equilibrium or even the equilibrium that we want to compute. So when we are actually playing the game in real time, we will search for an improved strategy that will give us a finer grained approximation of what equilibrium should look like. Now, let's look at perfect information games and single agent settings. Now, if you wanted to search in it, it should look something like this. You take some action, your opponent takes some action, then you're in some sub-game, but this remaining sub-game is too large to solve to the end of the game. Now, so instead, you just search over a limited depth, and at the end of this depth, you reach a leaf node and you estimate the value of that leaf node as the value of both players playing perfectly from that point forward. And if this estimate is perfect, then depth limited search will return an optimal strategy for the next few moves, and you can play according to that. Now over to Shubhesh.
In improper information games, this is not true. This can be demonstrated using a version of rock, paper, scissors called rock, paper, scissors plus, which is just like rock, paper, scissors, except if the other player chooses scissors, then the winner receives 2 points and the other loses 2 points. This is done to break the symmetry of the game. In this version of rock, paper, scissors, the equilibrium is to choose rock and paper with 40 probability and scissors with 20 probability. Here, we can observe a sequential version of the game where player 1 acts first and then player 2 acts without observing what player 1 did, which is why there are the dotted lines between player 1 and player 2 nodes. Let us say we were to play a depth limited version. We search as player 1 in this game and we do it in the same manner as perfect information games. So, as player 1, we look one move ahead and then we stop. Stop there and substitute the value of both players playing perfectly from that point forward. This is what that subgame would look like, and as it can be seen, if we try to solve this deflated subgame, there is not enough information for us to arrive at the equilibrium of choosing rock and paper 40 probability and scissors with 20 probability. We might always arrive at throwing rock. We might arrive at 1/3, 1/3, and 1/3, but there is not enough information to arrive at the equilibrium. The reason for this is because we assume that the player 2 is going to play the equilibrium strategy, no matter what we choose as player 1, and indeed, if that were true, if player 2 were to always play rock and paper 40% probability, then there would be a 20% probability that we could always throw rock and receive an expected value of 0. But in practice, that's not what would actually happen. If we were for example, to throw a rock with 80% probability, then player 2 would shift to a different strategy of always throwing paper, and the value of rock would drop to become -1. And so this idea of assigning unique values to leaf nodes works in perfect information games, but it does not work when you go to imperfect information games. In Pluribus, we explicitly acknowledge that players might deviate to different strategies other than the equilibrium. So when we are doing depth limited search, when we reach a leaf node and then give each player a choice between multiple different strategies that they could play for the remaining game, on the left, this is an example of what a sub-game might look like if we arrive at some root node where we cannot distinguish exactly what node we are in, and we do a depth limited search. Now at those leaf nodes, we allow each player to choose between multiple different strategies. 4 in this case of Pluribus, namely to play the blueprint or Nash equilibrium strategy biased towards folding, strategy biased towards calling, and lastly, strategy biased towards raising. By giving each player the choice of these different strategies, we train the model to be robust towards different strategies that the players might shift to if we were not to play in equilibrium. We now plot exploitability, which is just a measure of how far we are from Nash equilibrium on the y-axis versus the number of different strategies that players can choose at the leaf nodes at the x-axis. We find that in small games, this does in fact reduce exploitability as the exploitability is low. We are closer to an equilibrium in these subgames. We see that exploitability drops off quite dramatically as we add more and more strategies for the players, and of course, in the limit where we allow players to choose any strategy they want for the remainder of the game, exploitability probably goes down to 0, or should I say, the exploitability goes down to 0 specifically for 2 players and some games, but when you go beyond 2-player 0 sum, a lot of theoretical guarantees are lost. These graphs show the performance of Pluribus when it played with 5 other humans, all experienced poker players with over $1 million in poker winnings each. The dots show Pluribus's performance at the end of each day of play for 12 days. In the top graph, the lines show the winning rate in the solid line and the standard error is represented by the dashed line. In the bottom graph, the solid line shows the cumulative MVBS and the dashed line is the standard error for the same. it can be observed that Pluribus has a relatively steady performance over the course of 10,000 hand experiments, suggesting that humans were unable to find an exploitable weakness in the bot. Forms of self-play combined with forms of search have led to a number of high-profile successes in perfect information two-player zero-sum games. However, in most real-world strategic interactions involve hidden information and more than two players. This makes the problem very different and considerably more difficult theoretically and practically. Pluribus is an AI capable of defeating elite human professionals in six-player no-limit Texas Hold'em poker, the most commonly played poker format in the world. Pluribus's success shows that despite the lack of known strong theoretical guarantees on performance in multiplayer games, there are large-scale, complex multiplayer imperfect information settings in which a carefully constructed self-play with search algorithm can produce superhuman strategies. With this, we would conclude our presentation. Thank you.